Hey everyone, so this video is going to be on the convergence of series or sequences. So when we talk about sequences, we're going to be referring to, let's say, a sequence that we're going to call an. And let's say an goes from n equals 1 to infinity. So this is a sequence that takes natural numbers and sends them to real numbers. And when we say a sequence converges, we mean that the limit as n approaches infinity of an equals some number L. Granted that this L is finite, right? Couldn't be something called infinity or negative infinity. Now, when we talk about a series, well, a series is a sum. Okay? So, to be more rigorous, what we mean is we're going to define something called a partial sum. Partial sum is when you do the sum partially. So an example is, let's say we wanted to add a sub 1. I'm going to call this S1. I'm going to call S2 a sub 1 plus a sub 2. In general, I'm going to call Sn equal to a sub 1 plus all the way to plus a sub n. Right? In general, I'm going to use some notation to write this Sn as the sum from I equals 1 to n of a sub I. And this I equals 1 could be whatever the starting index is of our sequence, right? In general, it has to go from the beginning all the way to n. These are called partial sums. Now we can finally ask, what does it mean for a series to converge? Well, a series is asking you about an infinite sum. I equals 1 to infinity of a sub I. Now we can write this, as you might guess, by the limit as n approaches infinity of s sub n. Okay? This is something we can actually figure out now. If we want this to converge, once again, we require that it be equal to some number L that is finite. Now, while it may be easy to take the limit of a sequence, it is much harder to prove that the limit of a series converges. Whereas we have many tests for the limit of a sequence, such as possibly L'Hopital's rule, there are much more complicated tests that you need for the limit of a partial sum. So let's consider some basic examples. Let's consider the sum from n equals 1 to infinity of just 1. What this means is 1 plus 1 plus 1 over and over again forever, right? As one might guess, this is clearly going to diverge, right, to infinity. Let's try to rigorously prove that. So let's consider the partial sum, s sub n, which is going to be equal to sum from I equals 1 to n of 1. But this is just going to be 1 added n times, which is just n, right? So if we take the limit as n approaches infinity of s sub n, or just n, well, we know this is to be divergent, right? Pretty clearly. Things get a little bit more complicated when we consider something that's pretty similar, I would say, is n equals 1 to infinity of negative 1 to the n. This is equal to negative 1 plus 1 minus 1 plus 1 minus 1 plus forever, right? Now the problem is, you might say, oh, it's like 0 or 1, right? Well, the problem is we can never really tell which one it is. If we take the limit, it doesn't converge to anything. It keeps on alternating between 0, 1, 0, 1. This is kind of the same idea why we can't say the limit as n approaches infinity of sine of x or cosine of x converges, because they're constantly alternating. It doesn't close down on one value. So once again, we say that this series will diverge. even if it doesn't go to infinity, we can still have a sequence diverge, right? In this case, you might say it doesn't exist. And then finally, we'll give an example. N equals 0 to infinity of 1 over 2 to the n. Now, I'll give you the formula for this. And the formula for the partial sum, that I'll call Sn, is equal to 1/2 to the n plus 1, minus 1 over negative 1/2. There's a formula for this, and it's called the sum of a partial geometric series. Now, to take the limit as n approaches infinity, well, this 1/2 to the n, since 1/2 is smaller than 1, it's going to go to 0. So we're going to get negative 1 over negative 1/2, which equals 2. So we've shown that this sum converges to 2. Okay? So this one converges. Something you might have noticed when looking at these examples is, what was the limit of the sequence itself? So for this one, we had a sub n equals 1. Well, if we look at that limit, the limit exists, it's equal to 1, right? Now for this one, the limit technically doesn't exist, it's negative 1 or 1. Either way, my point is that they're not 0. And for this one, it is 0. If you take n to be infinity, you get 1 over 2 to the infinity, which you're just going to get 0, right? So it seems to be when our limit is 0, so is our sum. Now, this is not necessarily true, but there is a related theorem to this fact. Theorem. If the sum a sub n converges, and sometimes we will just not write the actual bounds of the sum, just to refer to summing over all of the sequence, right? Converges, then we know for a fact that the limit as n approaches infinity of a sub n must be equal to 0. Okay? I think a more helpful version of this is something that we like to call the divergence test, which will be the first of many tests you might learn to find the divergence or convergence of a series. The divergence test. The divergence test is actually the contrapositive of this statement, which says if the limit as n approaches infinity of a sub n does not equal 0, then the sum a sub n diverges. Now, I think this is pretty clear. Think about it. If the limit as n approaches infinity of a sub n was 2, let's say, then when you're getting towards infinity in your sum, you're just adding 2, 2, 2 all over again infinitely many times. Clearly, just like our example of adding 1 infinitely many times, that's going to diverge, right? The only possible way a sequence could converge is if its limit was 0. This has to be true for it to converge. It is not required, though, that if a sequence diverges, that the limit be 0. So what do I mean by that? It's possible to have a sequence that diverges and have its limit be 0. And I'll show you an example of that later on. So, the fact of the matter is, if you have your limit being equal to 0, it doesn't tell you that much. It tells you that maybe it's convergent, maybe it's divergent. But if it's not 0, that tells you a lot. That instantly tells you that it diverges. So there's a very helpful fact, the limit doesn't equal 0, and then there's a not so helpful fact, the limit does equal 0. Luckily, when the limit does equal 0, there's a somewhat decent chance that our sequence might converge. There is a chance. If it doesn't, there's no chance. So let's take this test and try to use it. So let's check if this infinite sum from n equals, let's say, 2 to infinity of n squared over 3n squared minus 5. Let's check whether it converges or diverges. So to check whether this is true, let's consider the sequence a sub n equals n squared over 3n squared minus 5. If we take the limit as n approaches infinity of a sub n, well, what we get is 1/3. You can get this from L'Hopital, or knowing that this is going to happen, or multiplying by 1 over n squared on the numerator and denominator. Either way, since this doesn't equal 0, our sequence must diverge. So we know this diverges. But let's look at one final example. Consider the sum from n equals 1 to infinity of 1 over n. Now this is called the harmonic series, and it's famous because clearly the limit as n approaches infinity of 1 over n equals 0, right? Okay. But like we said, the limit equals 0 doesn't tell us really anything. Only the limit not equaling 0 will imply divergence. The limit does equal 0 doesn't really tell us if it converges or not. And as you might learn, the harmonic series does in fact diverge. So kind of famously, its limit equals 0, but the sum diverges, which is very surprising. And I'll send out a video which will prove this in hopefully a couple different ways that might be interesting. Okay, hopefully that was helpful. Thank you guys for watching.